Bright Tuty. Every student matters.
Hello dear students, my name is Amit Ajmani and today we will be continuing up the chapter motion. In the previous lecture you must have observed, you must have seen that we have talked about the graphical derivations of the equations of motion, right? There were three equations of motion. First was V is equal to, the first equation of motion was V is equal to U plus AT. Second equation of motion was S is equal to ut plus half at square, and third equation of motion that we did was V square is equal to u square plus 2as, right, where V is the final velocity, u is the initial velocity, a is the acceleration, t is the time and s is the distance. We have already seen that. Okay. Now this is about our graphical representation. Now students, till now we have been studying about linear motion. When I say linear motion, I am talking about motion in the straight line. Fine. Motion in the straight line along a road. Okay. Now this particular linear motion may be uniform, may be non-uniform. Got it? In the uniform motion, we have said that the body is covering equal distances in equal interval of time, right. Let us take one assumption that now the body is basically traveling in a uniform motion along this rectangular field. Fine. Now when the object, let us give some names A, B, C, D, when the body is traveling from A to B, it can go uniformly. From B to C, it can go uniformly at the same speed, C to D also, D to A. But when it is taking this turn, its speed varies. This is what we have seen. Normally while we are driving also on the straight road, we can drive at a particular speed, but whenever we have to take a turn, we need to slow down, right. So when at these edges this particular object is taking turns, fine, it is a bit slowing down, or there must be some change in its speed, because the edges, the corners, the turns will inhibit its speed. In order to maintain a uniform speed throughout this particular tract, that means the body has to accelerate a bit. Fine, because its direction is changing at these edges, so it has to accelerate to compensate for these 4 turns. Now if I take a hexagonal path A, B, C, D, E, F, so now the direction of this body will be changing 6 times. What about octagonal? And I will increase it, and when I will take infinite turns, then it will become a circular path, right. Let us take it to be a normal circle. Fine. So this will be a circular path. Now whenever a body is moving in a circular path, and if it needs to maintain a uniform motion, a uniform circular motion, then we can relate by this particular concept that we have studied, we can relate that it has to accelerate in order to maintain the uniformity. Got it? So now very important thing, when we are talking about uniform linear motion, this uniform linear motion is not accelerated motion, but when we talk about uniform circular motion, it has to be accelerated motion. This is quite important difference between the uniform linear motion and uniform circular motion. When we talk about uniform circular motion, we are saying that from any point in time, that any place, let us say from A, if the body is covering this particular distance initially in 1 hour, then again it is going to the same path in another 1 hour and again in 1 hour. So, equal distances are being covered in equal interval of time. Every time the body is moving in a circular path, always it will change its direction, and because it is changing in direction, that means for maintaining this uniformity it has to accelerate itself at turns, right, fine. So, uniform circular motion is always accelerated motion, this we need to remember. Now, there are certain examples of uniform circular motion that we already know. Let us review a few. For example, the earth, all the planets, they are moving around the sun, right. Now, they are exhibiting a uniform circular motion, even though we know that actually they are not exact circular paths in which the planets are moving around, they are elliptical paths, but still it exhibits a uniform circular motion. Similarly, when we talk about the satellites, the moon, which is circulating, which is moving in a uniform circular motion around the earth, right. All the artificial satellites that we launch, they also exhibit uniform circular motion. In our houses, we see that clock, the minute and the second and the hour hands of the clock, even they are showing the uniform circular motion. Or in a circular path or a circular track, if an athlete is running covering the equal interval of in equal distances in equal interval of time, he is also exhibiting a uniform circular motion. Got it? Fine. So, these are a few examples of uniform circular motion. Now, quite importantly students, there are 2 or 3 things which you need to remember. The first thing is, whenever a particular path is moving in a uniform circular motion, at any point in time, at any place, the particular motion of the object is always a tangent to that particular point in which it is moving. Now, this thing we can relate by taking an exercise, an activity. Alright, let us take an activity to exhibit this particular thing. What we will do is, we will take a piece of thread and tie a stone to it, right, and from the center we will just allow this particular thread to move in a circular path, right. Now, what you do is, you allow this stone to basically get released at different intervals. Now, if you are doing it 3 times, 4 times, 5 times, you please observe that is the stone going in the same direction every time? No, it won't. But one thing is quite important, that the stone is going to take that particular path where it is exactly at this particular point. From there it is going to go in that direction. Fine. So, we can relate that it is always a tangent to that particular point where this stone is moving. Fine. So, an object, whenever it is showing a circular motion or it is in a circular motion, then at any point on that path, it will be, the motion of that particular object will be a tangent to that particular circular path. Got it? Fine. Now, important thing, you need to know that when we are just moving an object in any circular orbit or circular path, fine, then the force which is exerted from the center, that is known as the centripetal force, right. Just for your knowledge, I am telling you that it is the centripetal force that is exerted from the center. Now, we know that all the planets move around the sun. From where is that centripetal force coming? That is the gravitational pull or the gravitational force of the sun. Got it? Okay. Right. Now, we know that an object is moving in a circular path. Had it been a normal linear or a straight line motion, then we know that the speed of an object is calculated by this formula, distance travelled upon time taken. Got it? If we want to calculate the speed of this particular object in a circular path, then the formula remains the same, but we know that since it is travelling in a circular path, therefore, when we talk about the distance travelled by this particular object, we are actually correlating it and calculating it with reference to the circumference of the circle, right. So, when I talk about the distance, I talk about the circumference of the circle, and that complete one turn, if I am taking that complete circumference of the circle, we know is calculated by the formula 2 pi r, where pi is a constant whose values is 22/7 or 3.14. We know that, we have been using it, and r is the radius of this particular circular track. Got it? Divided by, of course, time. So, when we calculate speed or velocity of an object in a circular motion, we calculate it with the formula 2 pi r upon t. Got it? Fine. The unit remains, of course, same. The SI unit is meter per second, as it is of speed and velocity, and the bigger units may be kilometer per hour.